My name's Kevin.
I'm Lane.
I'm Jack, and this is Project 1, the helicopter problem. So the first step to solving the helicopter problem is to understand the problem first, because if you don't understand the problem, how are you going to do it? So to start with, the knowns are starting time, so t initial equals negative t, and the distance traveled, which is represented by d. Acceleration, so we're giving a function, acceleration over time, which is represented by this whole function right here. This whole function broken down consists of the x direction and the y direction. And this is each portion of this larger problem broken up just to represent the different directions. And these are both non-constants. Also in this problem, beta and alpha are known. The other knowns in this problem consists of delta x, which is equal to d, alpha, which is constant in y, beta, which is constant in x, and then t, which is a known time constant. So it's a constant we already know. Time is already represented. That's up, along with beta and alpha, it's up to the discretion of when you're solving the problem. It's up to the discretion, just because it's a real world type problem, so those values can change. The unknowns in this problem are time in the air, t, and vertical position, y.
Alright, so for identifying assumptions, for our velocity in the horizontal direction, there will not be a constant, and for the velocity in the vertical direction, there will also not be a constant. Another thing we can assume is that gravity won't be an influential factor, but also weight won't be accounted for too. In this equation of position, we have t final minus t initial equals distance, and we can assume that the helicopter doesn't contain any passengers as well. But what we want to know is the time spent in the air, which can be found by t final minus t initial, or in other words, just time. To find where the location lands, we can do change in x is equal to distance, and the change in y is equal to an unknown quantity, which will be later addressed to be equaled in meters.
All right. So the third part of part one of this problem is representing it physically. So we drew a little diagram where this is the helicopter. It's amazing. And it travels a known distance, or delta x, d. And it will land at a delta y, and since we don't know what delta y is, it could be either positive or negative. We represented that as just delta y in either the positive or negative direction. This is the positive y, that's the positive x direction. And we know that it starts at t equals negative capital T. So we used our knowledge of the equation to come up with three graphs representing acceleration, velocity, and position. So for the acceleration graph, we determined that since neither create a constant acceleration, it will result in most likely a third power graph, and that would in turn result in another higher power graph of velocity, which is going to be the slope of the acceleration, and then position, which is going to be the slope of velocity. In this case, we just assumed that the position will always be positive, but as factors such as alpha, beta, and capital T change, that is subject to change. These are just rough estimates of what it might look like.
So after part one, as we have explained, this brings us to making sense of our work. And part A here, are the units correct? Well, all the units will be based off of what has been previously explained by the video, which has worked the whole problem. So, to start, the units are correct. I mean, there's only one way to get the units correct, really, I guess, on this problem. But first, we start with delta x, which is change in x. This is 2 beta t squared divided by 3. Beta will be in meters per second squared. And our distance, which will be the sum of all of this, that will be in meters. So then that brings me to explain delta y, which is our change in y. Alpha divided by 35 beta times d will give you your acceleration constant. And alpha in here will be defined as in meters per second squared. Beta will also be in meters per second squared. Those two, for clarification, those are the units, but there still needs to be numbers input. Then capital T, which is in seconds, can be explained by the square root of d divided by beta, and that's in meters, and that comes down to seconds squared, square rooted, which is just equal to seconds.
Okay, so this is 3B, and I'll be explaining if my numerical answer is reasonable for the problem. So this makes sense because as you integrate the acceleration and velocity, you can solve for distance. Then you can plug in the numbers to see if your problems make sense. And I did that below. So for this example, in the change of x vertical direction, we see that it can also be equal to distance of this equation where I found numbers for beta and time to see if it would make sense. And these numbers came from my research, where I found that a good number for a helicopter's acceleration is 45 meters square, and for t to be 5 seconds. After plugging all of that in, we got 750 meters, and it would make the most sense because you take 5 times 2, which is 10 seconds, and in 10 seconds of it being in the air, it can travel 750 meters, which is equivalent to 7.5 soccer fields. And in this in this example, we see that the change of y, which is the vertical distance, where we have 3 quantities. One of them is a, it's 15 meters seconds square, and beta and distance. Distance is taken from my change of x example, and beta is also from my change of x example. So we plugged all of those numbers into this equation, and then it came out to be 14.29 meters, which is equivalent to 3-story buildings, which makes sense for the uneven terrain on Mars.
So this takes us to 3C, which is does your symbolic answer make physical sense? So the symbolic answers that the professor had previously found was that as the change in x, delta x, is equal to 2 beta t squared over 3, which is also equal to d, which is the distance constant. And then there's delta y, which is equal to alpha over 35 beta times d, which could be also written as 2 alpha t squared over 105. So using covariational comparisons, we can determine that as beta increases, delta x increases, but delta y stays the same. That makes sense because beta is a constant in respect to the x direction. So it changing should not have an impact on the y direction. And same goes for alpha, which is alpha increases, delta y increases, but delta x stays the same, which is just the same but opposite. And as t increases, both values increase. And that's because t squared is in the numerator of both. So as t goes up, the expected values for both change in distance horizontally and vertically would change, increase, which makes sense because as time increases, it would be expected that the helicopter would travel further in both the horizontal and vertical direction if there's still acceleration in the vertical direction.